In this video, I'm going to give a short demo of the address sanitizer. This is a code sanitizer that's supported by both the GCC and Clang C++ compilers. And what address sanitizer does is it checks for various types of bugs which relate to memory, things like memory leaks or accessing memory locations that you shouldn't be accessing, for example, memory that you've freed and deallocated that you're continuing to still access, things of this nature. And these are often very nasty types of bugs, difficult things sometimes to even detect and track down. So address sanitizer can be quite helpful. So for the purposes of this example, I'm going to use some code in a Git repository on GitHub. And this is a publicly accessible repository, so if you want to clone it yourself and walk through the example on your own, you can certainly do so. The particular example that I want to look at is in this subdirectory of the repository, so I'm going to change directories there. If I take a look at the files that are in this directory, there's basically just a C++ source code file and a CMake list file. If I look at these files in more detail, if I look at the C++ source code file, we have a relatively simple program. It's creating a vector of integers with the values 1, 2, 3. It's then doing a find operation to try to locate the value 2 in the vector, and 2 is in this vector, so this is going to return an iterator which refers to the value 2. So if I dereference this iterator, in other words star TWO, something like this, presumably this would give me the value 2. But in the interim between when I get this iterator and I actually dereference its value and print it, I am doing this loop here where I'm adding a bunch of things to the vector. It turns out there's a very, very serious bug in this program, but it might not be obvious to you that there is such a bug, and address sanitizer will be very helpful in helping you to detect the bug even though you might not notice it. If I look at the CMake list file, there's not really anything too notable here. It's just your standard plain vanilla CMake list file without anything too fancy. So now I'm going to build the program with CMake. So first I'll do the configure stage, and I'm going to use the CMake build type of debug. So it's a debug kind of build. Then I'm going to actually build the code, do the build stage of CMake, and then I'm going to run the program. And what we'd expect the program to do if it's working correctly would be to print the value 2, because essentially what it's doing is it's getting an iterator that refers to the value 2 and then it's printing it out at the end of the program. But what we end up getting is it prints the value 0. So something's obviously wrong. It's not doing what the programmer probably intended for it to do. But again, if you look at the code more carefully, you might be able to figure out what's wrong. Hopefully you can. But if this was part of a bigger program, it might be more difficult to spot this particular bug with more lines of code. So address sanitizer is very, very helpful for detecting these sorts of bugs. So I'm going to go back to my CMake list file here. And what I'm going to do is I'm going to add a few extra lines to it to enable address sanitizer. So essentially I've added these 2 lines here, well, ignoring the comment that precedes it. And what I'm doing here is the CMake variable CMake CXX flags. This specifies extra compile flags that are used when you're compiling C++ source code. And I effectively have appended to the list of the flags that are used this flag here, minus F sanitize address, which enables the address sanitizer. And also I've added to the linker flags, these are flags that are used when you're linking your program, I've added the same option to the linker as well. You need it for both the compiler and linker. So I'll save this and exit, and now I'm going to rebuild the program. So I'll use CMake again, doing a debug build, do the configure, and then I have to actually build the code with the build option to CMake, and now I'm going to run the program. And now you'll notice something very different happens. My program is violently terminated, and I get a lot of debugging output printed out. The main part to look at is the very first part here that's printed out. It's saying address sanitizer has detected an error. It's saying the particular type of error is a heap use after free. The heap is where when you're doing dynamic memory allocation, memory is allocated from the heap. Like for example, when you use new and delete, you're basically doing allocation and deallocation on the heap. And it's bad news if you try to use memory after you deallocate it. Once you deallocate it, you're not allowed to access it anymore, and basically this program is accessing memory after it's freed it. And it gives us a whole bunch of information that's helpful for debugging. In this particular case, it's saying the place where this heap use after free is occurring is on line 12 of app.cpp. So if I go back and look at the file, the source code file here, this is line 12. So it's saying here on this line we're actually accessing memory that we've already freed. And if you haven't figured out what the bug is in this code already, what's essentially happening here is that, again, we have this vector with these three elements, 1, 2, 3, and we're searching for the value 2 with this find operation. This is obviously going to find the value 2 because it is in the array, and it's going to return an iterator which refers to that value. If we immediately printed out the value, everything would be fine. This would just print a value of 2 when we dereference the iterator. But the problem is this intervening code here. We're using pushback to add a bunch of elements to the vector, and pushback can invalidate iterators that refer to elements in the vector. So essentially what's happening is, due to these pushback operations here, the iterator that we've initialized here is no longer valid by the time we get down here, and it's pointing to memory that's already been freed. So this is what causes the problem. But again, well, maybe for some of you, even if you're kind of like newer to C++, it might take you a while to figure out why things are not working there, even when address sanitizer is pointing you to the line where things are not working properly. But if you imagine that even if you're a more experienced programmer, if this is a much larger program, tens of thousands of lines of code, there's lots of potential problems that you could have with bugs pertaining to memory. They're often very difficult to detect in the first place, and sometimes very difficult to track down. And this gives you a way to very quickly identify them and be able to resolve the bugs much more quickly. So again, I highly recommend the use of code sanitizers. In particular, address sanitizer is probably one of the most important ones to make use of. So that ends this demo.